Hi, my name's John Downing. I'm a limnologist and an ecologist, and I created a series of sessions talking about various aspects of aquatic ecology and limnology. This session is entitled Water Physics, Waves, Currents, and Seiches, and this is session 11 of the aquatic ecology series that I have created. If you look at a small lake or a little pond, it looks pretty calm. But basically there's a lot going on in this system. Even though it looks like a glassy surface, there is some substantial movement going on, usually at all times in aquatic ecosystems. In other systems, it's extremely obvious that there's a lot going on and that there's a lot of physical movement. This is Lake Superior and some waves on Lake Superior. I'm going to show you a couple of videos just to get you sort of in the mood for thinking about waves first, and then we'll move into other kinds of waves and talk about currents and a variety of other aspects of water motion in aquatic ecosystems. So this is a video from Lake Simcoe, and I used to do this lecture or this session with waves going all the time, and I stopped doing that because people began to get kind of seasick as we'd go through the class. But you can just look at these. Now, clearly, you're seeing some fairly gentle wave action toward the shore. You see the waves pile up a little as they get close to the shore. Also, if you're paying close attention, out there directly ahead, some distance offshore, you can see some kind of a disturbance. Do you notice there how the water begins to pile up a little bit higher and seems to be disturbed? Likely there's some sort of a reef or shallow bottom there. But mostly the waves move along in a progressive way. Now they're moving, the waves are moving, they're not moving the water. It's very much like you would hold, say, a jump rope with on two ends and create a wave in that jump rope. It's not the rope itself that's moving, but the wave is traveling along the rope. So it's very much the same here. Now that's not to say that water doesn't move when there's wave action, and we'll talk about that in just a little while. But it's important to know that it isn't fully moving all of that water. Now here's another kind of more substantial sort of wave. This is a much less gentle wave on Lake Superior, and Lake Superior is well known because it's extremely large. It's known to create substantial wave action. I believe they probably took out the audio and added classical music, probably because people on board were screaming. Maybe not. It's wave action can be quite unbelievable. The amount of energy contained in those waves can be destructive, and it certainly is always powerful. So there are things you probably already know about lake physics, and just like to review a few of them, and hopefully you're going to learn a lot more in this next session. But one thing you've probably learned is that wind and waves are quite closely related. And also, if you've done any boating at all, you can get out of the big waves if you are getting bounced around too much by going behind an island or point on a lake. This goes to the question of fetch and its effect on wave power. Also, you probably have watched water move along beaches in some sort of direction, and that direction is often determined then by winds and currents. And then another thing you may have noticed is if you float in the water in the shallows on a windy day, the waves are going to move you back and forth. There's a rotational sort of motion that moves you back and forth. And if you've ever been diving in relatively shallow water, you may be moved quite some distance back and forth by the rotational velocity of the wave motion. So lots of things you probably already know that you've observed, and I hope that you'll think about many more. Now here are my objectives for this session, and there are many, but many others that we'll sort of pick up along the way. But I'd like you to first off learn the concepts of lift, vorticity, Coriolis, and particle sorting. These are 4 basic concepts that go to the importance of waves and water movement. I'd like you to also learn the major sources of motion in lentic ecosystems, and lentic here is used sort of advisedly, that when wind is blowing, lake ecosystems are not moving necessarily very slowly. I'd like you to learn also how wave forces sort sediments. I'd like you to learn about the importance of fetch, and then I'd like you also to learn how lakes rock back and forth sometimes, either the surface or at the hypolimnion. And that action is called the Seiches. These are some of the things I'd like you to learn today. Now, physics may seem difficult, and please don't be intimidated by what we're going to talk about, because it's really important. Physics mixes nutrients and materials around lakes and ponds. If it weren't for that, then organisms would deplete their nutrients and gases and other materials that they need simply by taking them up around them. Physics also renews gases, or fails to. Well, we've talked about that when we talked about hypolimnia, that the gases down in the hypolimnion are pretty much set until physics will then renew those gases by mixing the lake water column. Also, physics determines materials found on shores, and if you're interested in various kinds of shores, you probably noticed that some places are kind of muddy and other places are sandy, other places are rocky. That's because of lake physics. It also leads to presence or absence of good habitat. Now, organisms normally need some kind of intermediate habitat. They're not very good at functioning in a extremely dynamic environment, but there often needs to be some kind of motion in order to move the sediments away and renew gases, so that the waters can provide good habitat. Also, physics explains much about what goes on biologically and ecologically in aquatic ecosystems. So it's very important, and not to be intimidated. And actually, everything I'm going to show you is fairly straightforward and simple, and I hope that you'll find it easy to learn. Now, I want you to learn also about particle sorting. And when I talk about particle sorting, I personally like to talk about cookies. Because one of the kinds of particles you find around frequently would be cookie crumbs. And those cookie crumbs, if you get them all over your desk or your clothes, you want to get them off of there probably so that you don't seem unkempt. But the way you often do this, isn't it, by blowing or moving some velocity of medium across them, and that medium picks them up. And picks up those cookie crumbs and moves them. I think no matter how hard you blew on an entire cookie, you'd be pretty unlikely to be able to move it. And this should teach you a basic principle that smaller particles are far easier to move than large particles. What this means is that forces are going to move the small things first and the large things afterward as they gain in strength. And so if you are in an area where you see a lot of large rocks, the first conclusion you can draw from that usually is water or wind or something has moved away all the smaller particles. Now, another concept I'd like you to learn is lift, and you need to believe in lift, because if you didn't believe in lift, you'd never fly in an airplane. And lift operates in aquatic systems too. Lift is a partial vacuum that's created above the surface of an airplane's wing or any other sort of bump like an airplane's wing. And this partial vacuum causes the wing to be lifted upward. The special shape of airplane wings, like an airfoil, is designed so that air flowing over it will have to travel a greater distance and go faster, and that results in lower pressure at the top, resulting and thus lifting the wing in an upward direction. Lift is that force which opposes gravity, and you can see that down here on the bottom. The airplane wing is curved up, and this looks surprisingly like, let's say a rock in a stream, or like a bump in the water, or maybe even a water wave. As air moves up over it, it will tend to lift at this point, and while supporting the wing on the bottom, and that causes this is a mechanical force that causes anything over which you have an airfoil sort of effect to be lifted upwards. So this is another really important concept. Now Coriolis is and we'll see several images of Coriolis effect. Coriolis is the tendency of objects that are moving straight to curve due to the rotation of the Earth. And here we're looking down from the North Pole, at the North Pole, with a stationary camera, and an object, or let's say a particle of water or anything else, is acted upon by some force. It in fact will, in the northern hemisphere, curve to the right, or appear to curve to the right. It actually is going straight, but it will define a line that is curved. It will actually move in a way that is curved with respect to the moving medium. So watch this just a little bit and see. You can demonstrate this for yourself with a piece of paper, with a pencil stuck in the center of it. Rotate the paper around while a friend moves a pen in a straight line, and you'll notice that it describes a curved arc on the surface. This means that in the northern hemisphere, particles tend to move to the right. In the southern hemisphere, they will curve to the left. Now, vorticity is another, and actually I have a few more. I'll show you some more on Coriolis in a second. But vorticity is something that you'll observe in funnels and toilets and tornadoes and so on. And it's kind of related to the Ekman Spiral that we'll talk about in just a minute. But planetary vorticity in general is a tendency, again, for water, let's say, moving downward or moving in any direction to twist. And it twists for a couple of reasons. One would be Coriolis effect, and the other would be simple shear. And so any kind of water that's going in a straight line will have a tendency to try to spiral, and that is vorticity. So those are four major concepts that it's important for you to learn. There's major motion in lentic ecosystems, and we'll talk about a fair number of them as we go along today. But basically, many of them are driven by wind stress across the surface of the water. Wind moving from one side to another. There are sheltered areas and exposed areas. Wind exerts stress on the water, and this transmits a substantial amount of energy into the water, and that drives a great deal of different kinds of motion, including things like upwelling, interleaving of waters. We'll talk about Kelvin-Helmholtz billows. There also are gravity waves, oscillating boundary layers, seshing as water rocks back and forth. There is underflow, various kinds of microstructures, and and also sort of compression of isotherms. We talked about isotherms when we talked about thermal structure and so on. So lots of different kinds of energy and physics operating in lakes all the time. So we're going to talk about surface currents. We'll talk about surface waves. We'll talk about a thing called Langmuir circulation, also some standing waves, and the standing waves will be surface Seiches or internal Seiches, and also some internal progressive waves. Now, waves at the surface are called progressive waves. There are waves inside of lakes as well, and we'll talk about some currents caused by water influx. So the first thing to understand, and this looks really complicated, and one of the basic things that scientists do when they don't want you to understand something or keep the club to themselves, I think, is to use Greek lettering. Here we have thaw air and thaw water. Now, thaw air and thaw water are the stress that air exerts on water, and thaw water is the stress that water exerts on air. Going on to define a few more little variables here. Rho air, we have rho air and rho water. Rho air is the density of air, and rho water is the density of water. And mu, this little U-looking thing here, is the velocity of air and the velocity of water. Now, the stress that air exerts on water is simply the product of the density of air and the square of the velocity of air, and that will be the stress that air exerts on water. The stress that water exerts on air, just by analogy, is the same kind of thing. It is the stress, it is the density of water times the square of the velocity of the water. And that is the stress that water exerts on air. Now we know that because energy needs to be conserved, that the stress that air exerts on water needs to be equal to the stress that water exerts on air, and so we can simply down here set those values equal to one another, and simplify the equation and by rearranging. And this means then that the ratio of the density of air over the density of water is equal to the square of the velocity of water over the square of the velocity of air. And rearranging, because we know here that what the density of air is, here as 10 to the minus third approximately, and the density of water as 1 gram per cubic centimeter, we can calculate the velocity that's transferred, the ratio of the velocity of water to the velocity of air. So if we're moving, and that has to be 0.03 or about 3%. So there's a take-home message that if we're moving air across the water, let's say at 100 kilometers per hour, then we know that the velocity transferred to the water has to be 3% of that, or about 3 kilometers per hour. That's a pretty substantial clip, but a 100-kilometer wind, I think, is about a kilometer per hour. Wind is something like 60 miles an hour is a fair wind, but I think you'll appreciate that regardless, still 1 kilometer per hour is still pretty fast, and especially currents are measured in things like meters per second, and even a gentle wind can move a substantial amount of water in a current. So surface currents are formed by the effect of wind, and the surface currents are pretty reliably plus or minus 0.01, depending on the relative temperatures of air and water, about 3%, something like that, between 2 and 4%. You can see that here's the wind factor and the wind wind velocity. This is the percentage, and here the percentage of the velocity transferred to the water. And when the wind velocity is extremely high, then of course we don't get the same percentage simply because it takes time to generate that wind velocity. But generally, somewhere between about 1 and 4% of the wind velocity is transferred to the water as a current. So there are currents in lakes, even in small lakes, although if the wind velocity is low and the lake is small, the current will also be rather low. Now, we've already talked about the Coriolis effect, but those currents tend to turn, and they turn in two different ways. One due to the motion of the Earth, and I'll show you another video on that, and one due to something called the Ekman Spiral. So this is a video, again, about the Coriolis effect that you might find amusing. So I'll just leave it to this narrator.
Slightly, I'm going to rotate the merry-go-round counterclockwise. So you throw it whilst it's moving. What's going to happen?
I don't know why, but I feel like if we're going fast enough,
yeah,
like I might actually be the one catching the ball.
Okay, so you're going to throw it and you're going to catch it. All right.
Yeah.
Right. What's going to happen, dude? Oh, it's going to veer off to the left. So the ball is going to swerve off to the left. Yep. And you might catch it. Possibly. Okay, good. Right, so what's going to happen?
I think it's just going to come straight to me and I'm going to catch it like the champion that I am.
Show me the catch. Okay, great. Right, okay, so everyone, no, hang on, one more.
He's
Spencer.
not arrogant.
Just quietly
He's
confident.
not catching it. He's
Really?
not catching it, no.
So what's going to happen to the ball?
I'm catching it. It's right here.
Great, so we've got one saying to go off to you, one saying to come to you, Spencer, and you think it goes straight ahead, but you think you'll be the one catching it.
Yeah.
Now remember, the ball will be thrown straight across the spinning merry-go-round, but where will it end up? Will it be caught by the thrower? Will it be caught by the person opposite? Will it be caught by the person to the thrower's left, or by the person to the thrower's right?
Right, in your own time, throw the ball.
I got this. Oh!
So the answer was D. It was caught by the person on the thrower's right. Our camera angles seem to show the ball bend in the air. So is that a camera effect, or are we seeing what they saw?
Hang on, this couldn't get much more simple. The idea was just to throw the ball straight to Victor to show us his amazing catching skills.
That's right.
Yeah, it did. It just curved right over this way.
So let me get this straight. So you threw the ball, it left your hands, and then what?
And then it just got sucked over to him.
In the air.
Yeah, I threw a perfect throw.
What did you see?
Yeah, curved right in it.
Right, so we're all agreeing here the ball curved in midair.
Yeah.
Yeah.
And you didn't cheat this at all.
No, I didn't.
Okay. And do you know why it did that?
No.
No idea. It's called the Coriolis Effect. And it's very simple. It's objects in motion appearing to be, it's an optical illusion, appearing to be deflected off their intended course. So what's actually happening here is you are throwing this ball. You can only throw a ball in a straight line. Can I clear that up straight away?
Yes.
Even though it appears in your eyes to be bending. So you throw the ball straight, it's still going straight, but the table is moving below you, and all of a sudden, look who's in front of that straight moving ball, and it looks like it's bent off to the right because you're still looking at the guy you were intending to throw it to, and that, ladies and gentlemen, is a Coriolis effect.
Just another demo of it. Now, when the Coriolis effect, the Coriolis effect has a tendency then to move the surface water. Here we see a spiral of currents. This is called the Ekman Spiral. And normally, when the wind is going one particular direction, then the surface current velocity is going to be twisted to the right in the northern hemisphere by about 45 degrees. So, if the wind is going from north to south, that means it's going toward 180 degrees south, and it's bent away from that. The surface current then would be bent away from that to the right in the northern hemisphere, and so would be going 225 degrees in the direction of 225 degrees on the compass. So you deflected to the right, the currents are deflected to the right by about 45 degrees. So a wind directly from north to south would have the currents going to the southwest. Now, the other thing that happens is because of the Ekman spiral and because of the Coriolis effect, the water volume moving downward must be balanced by return flow, and there is a null point at some place, like here, right there, where there is no net flow. But generally, that water will move in a spiraling way in order to balance energy, and also because it's twisted down by this Ekman Spiral effect. This is the same kind of effect that causes storms to twist, sort of hurricanes to twist in a clockwise direction in the northern hemisphere, and well, in any case, it's the same kind of same kind of effect. But that's neither here nor there. But what's happening is we've got a twisting downward, so that you don't have the same velocity everywhere. If you did, I mean, same direction of velocity everywhere. If you did, the whole lake would have a tendency to pile up on one side. And so there are, if you can just imagine the major forces that are going on in lakes when these currents are flowing. Now, the Ekman spiral also interacts with stratification, because stratification has a tendency to change the flow of water. So the wind velocity is in this direction, then the surface flow is to the right of that in the northern hemisphere, and this is an unstratified system. The water begins to twist around until you get down here, and will actually come all the way around in a double twist and be flowing at very deep depth backwards. Now, if we have a thermocline at 13 meters, then of course that pretty much stops the flow of water, and because there's a strong barrier to transmission of energy downward into the deeper water of the lake. And so if the same lake had a thermocline at about 13 meters, you'd see a completely different sort of Coriolis, a different kind of Ekman spiral. The same demonstration is here along the right. We can see different flux rates of water in different directions, whether we're looking along the wind axis or the vectorial forces across the wind axis. So here we have relative stability. Water movement tends to stop at high relative stability, and if we look along the wind axis, we'll see a different array of velocities than we see across the wind axis. The next thing I'd like to show you is a demo by Gigi Richards' geology class. This is a demonstration she gave for Geology 103, and you can just see the same kind of thing as she explains it over in about a 3 or 4 minute video.
Hi class, our next video is about the Ekman Spiral. I've had a couple questions about this and just wanted to make sure we were all clear on what was going on with it. So I'm going to show you a video that's actually from your interactive videos from the My Meteorology website, and we're going to talk about the Ekman Spiral here. So remember, ocean currents are set up by the fact that wind blows over the surface of the ocean, and there's some friction between the wind and the ocean. And so the wind, the air moving over the ocean surface, is going to drag that surface of water with it. And then the next level water is going to drag the layer of water below it with it. And the next layer of water below that is going to drag that next layer of water below it. And so what we have is sort of a cascading effect from the wind dragging the water, and one layer of water dragging the next layer of water, and the next layer of water dragging the next layer of water. And basically your velocity is going to decrease as we move from the ocean surface down. But we have another effect, and that is the Coriolis Effect, which of course in the northern hemisphere is dragging those ocean currents and wind currents to the right, and in the southern hemisphere to the left. So let's watch the video. So here we have the wind that's pulling this ocean current, and it's being deflected by the Coriolis effect. And as we go down in depth into the ocean, so this cube here is essentially a cube of ocean water, and the arrows are vectors showing the velocity of those ocean currents. So if we look down from the top, this square here is saying let's look at the top view. So we're here and we're looking down in plan view. And in plan view we can see, let me pause it here, we have the wind blowing in this direction, and then the surface is headed off to the right. We're in the northern hemisphere. The Coriolis effect is pulling it off to the right. And then as we go down in depth, we're going to go further and further and further and further to the right, but those arrows are getting shorter because the velocity is decreasing because there's less and less effect from the wind as we go deeper into the ocean. And so the net effect of the wind blowing in this direction and the Coriolis effect pulling it in this direction is that the net Ekman transport is to the right in the northern hemisphere. So the reason that we call it the Ekman spiral is that if you traced the end of these arrows, it actually creates a shape like a spiral. So the magnitude of the velocity decreases as we go deeper, and the direction is forced more to the right with the Coriolis effect. So the net effect along a shoreline is in the northern hemisphere. If we have the wind blowing this direction, our deflection is going to be to the right. So that's what the blue arrows are showing. So the surface water is going to be moving away from the shore. And because that water moves away from the shore, then you're going to get some deeper water is going to move back in to replace that surface water moving from the shore, and that's what we call upwelling. So we have this deep, cold, nutrient-rich water that's going to upwell at the shore as that warm surface water moves away from the shore. And then if we change the direction of the wind, now in the northern hemisphere, that surface current is going to move toward the shore, and you're going to have downwelling because that current moves to the shore. It's a mass balance, right? That water has to go somewhere. So if the water moves to the shore, it's got to go down, and then it's going to go away in the deeper current. And if we switch hemispheres, let's switch hemispheres. So now, if we're in the southern hemisphere, the deflection's to the right. So the green arrow is showing the direction of the wind. The blue arrows are saying the surface water is deflecting to the left, and the purple arrows are showing the fact that now we have upwelling because the wind is pushing the water to the north, the Coriolis effect is pulling it to the left, that surface water, and with the Ekman spiral we have a net movement to the left at the surface, and then eventually we have to have that deep water coming up, that deep, cold, nutrient-rich water replacing that surface water, so we have upwelling. So that, in effect, is the Ekman spiral and its relationship with the hemispheres and upwelling and downwelling.
And the same factors, upwelling and downwelling, occur in lakes as well as seas and operate in exactly the same way. Of course, the wind forces tend to be larger in oceans and seas because they, in fact, are larger. Now, lake currents are generally due to the wind's work, and under calm conditions, you still have some motion, and you'll have essentially eddy diffusion of particles sort of moving up and down. So it's not completely calm, but when wind is blowing on the surface of a lake, again, 3% of the wind velocity will be transmitted to the water, and because the wind can't pile up or make a big hole, pile up on the windward side, or make a big hole on the leeward side, then this water has to move back in some way, and does so through currents below the surface, normally above the thermocline. Now you can have an exposure of the deep water, the hypolimnetic water, if winds blow hard enough, and we'll get to that in just a moment. So the winds can destabilize thermoclines and cause mixing, and because we are moving a lot of velocity oftentimes along that thermocline, we're moving a lot of water, we can begin to erode away at the thermocline and cause some other currents there called Kelvin-Helmholtz billows that we'll talk about in just a bit. And now, empirically, of course, this is a relationship between stability of the water column, which is inverse to wind velocity, essentially over a bunch of years. And here you see algae growth. When stability is high, algae growth tends to be high. When stability is low, algae growth is low. And Daphnia, or the things that eat the algae, tend to, these are cyanobacteria, tend to be in much better health and grow much better when when the water column is less stable. So this can have an effect on the ecology of systems as well. Now, where do waves come from? And this is where we get this concept of lift and also some sort of downwelling pressure. These arrows here are, except for this one here, are arrows of force, basically showing how the forces are distributed. Wind will blow across a surface and it will find some kind of minute disturbance. If it doesn't find a minute disturbance, it doesn't really matter very much either, because the wind will begin to go slightly slower along the surface of the water due to drag. The faster winds up above will then curl back down here and make a little dent, and that can start a wave. So a minute disturbance or a dent caused by the drag of the water surface can also get these waves going. Now, because we have a little bump here that's formed by either of these processes, then we're going to get lift that's generated. And so we'll see some lift generated on this piece of the wave, lifting it upward. This downward motion will tend also to push back slightly against the wave, helping it to pile up. So these will be forces moving the wave. Now, when air hits the base of the wave, it's pushing the water downward and forward and creating this traveling wave. Likewise, lift picks up the wave and accelerates the air over the top of it and making a pushing downward here and backwards and making that wave move along the surface of a lake. You'll get waves in almost anything, and there are and you'll see different kinds of waves. Now, waves don't go uniformly all the way across a water body, of course. Not the same wave. They tend to be they don't form one big row that moves progressively across a water body because of other kinds of forces and the uneven force of wind on a lake. They'll go at different velocities, and we'll have sort of some sort of looks like a big long progressive wave, but it doesn't really happen like that very often. Now, surface waves are called gravity traveling or progressive waves, and you may make several measurements on them, and you might think to yourself right away what the biggest wave you've ever seen is on a water body. Think about how big it was, and especially important if it's on a lake, because I want you to think about the sorts of magnitudes of forces that you'll see on lakes. And many times when I ask this question, what's the tallest wave you've ever seen? People will say something like, 3 feet waves, a wave of about 3 feet tall. And we'll think about that in a second. But what that means is the distance from the peak to the trough would be about 3 feet or about 1 meter. Now, a 3 foot wave, I'll tell you right now, is a very, very large wave indeed for most kinds of lakes. A very small wave for the sea. And if you're interested, you can listen online to the various reports of waves and wave heights and so on from various marine observatories. They tend to be pretty big. Lakes tend to have smaller ones. Now, we've talked about wave height. We should also talk about wavelength. What is the wavelength? That is the distance between the two peaks, or distance between the two troughs. It doesn't matter which one. Basically the distance between any two identifiable features, assuming that all waves are identical. So that's wavelength and wave height. Next time you're sitting next to a lake, estimate with your eye the wavelength. It'll allow you to make some pretty good guesses about other kinds of wave characteristics too. Wave height and wavelength. Let's see. We seem to have moved spontaneously. Okay, wave period is the time it takes between the passage of adjacent wave crests past a stationary observation point. And so you can measure the velocity of the waves, usually measured in meters per second. It's the rate at which the wave crests move forward. So wave velocity you can think of as, when you're hearing waves on a shore, you'll hear it as a swash, 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 swash. That will give you the wave period, and then if you know the distance between the wave, between the peaks of the waves, then you can calculate the celerity or the velocity in meters per second. Now here are some gravity-wave relationships, and again, don't get too carried away with how. Hang on, guys. Don't get too worried about these equations. Velocity is the ratio of the wave length to the period, and it's measured usually in meters and seconds. That gives us velocity in meters per second. Now, again, for all surface waves, you can calculate the velocity fairly easily by the equation that you see below that, but you need to know a few things. What you need to know then is the wavelength, clearly, and you'd need to know the depth of the water approximately, or actually exactly. It's not hard to measure. And you'd need to know little g, which is acceleration due to gravity, which is measured in meters per second, and tan h is a hyperbolic tangent. Given that relationship, if you know the wavelength and the depth, you can calculate the velocity. Now for deep water waves, now when you're out deep in a boat where you're at a depth z greater, or z or z greater than the wavelength divided by 2, that's our definition of deep water, then the velocity can be calculated much more easily, simply from the wavelength and acceleration due to gravity. And there's a very simple equation to the right. Basically, the velocity in meters per second will be equal to 1.25 the square root of the wavelength in meters. Now for shallow water waves, this is because it's quite important to realize that waves, as they move along, if they hit obstructions in the shallow water, much like you saw in the Lake Simcoe sort of gentle waves, there was something shallow there that was causing disruption and actually a piling up of the waves on the bottom because of the conservation of energy, then the velocity is equal then to the square root of g, acceleration due to gravity, times the depth, z or z. And this is shallow water waves are defined as waves in waters where the mean depth is less than 1/20th of the wavelength. So that's quite shallow. And then over at the right-hand side on this, and you can find these also in the Calf limnology text, there's some rules of thumb, and the wavelength is usually about 20 times the height of the wave. So if you know the wavelength, which is sometimes easier to measure than the wave height, then you can calculate the wave height. The maximum wave height in meters is approximately 0.332 times the square root of the fetch. Now the fetch is the distance in kilometers across a lake on which the wind can operate unimpeded. So, in fact, that is defined in a previous session. So fetch is an important measurement, and we'll see some more fetch relationships in just a moment here. Now, fetch determines wave height and period, and recall that fetch is the distance across the lake, across a water body that wind can operate. We can calculate, if we know the fetch and the wind velocity, we can calculate the wave height fairly directly using this empirical set of equations from a book by Hoekensen and Janssen, and where the wave height is equal to the square of the wind velocity divided by g, acceleration due to gravity, times 0.0026, a constant, times this ratio that you see in this equation, where the constant 0.47, or the exponent 0.47 is determined empirically. Now the wave period can also be calculated. These are fairly interchangeable kinds of calculations in a very similar sort of way. So if you know the fetch and you know the wind velocity, then you're in pretty good shape to calculate the wind height, or the wave height, and the wave period. So you'll know how high and powerful the waves are, and you'll also know how fast they're coming in. I've used these kinds of measurements in order to help design lakes, and this is for a smallish lake, and you can see this the scales there in meters. This is a fetch in meters for a south and northeast prevailing winds. So as you can see, the fetch, because the winds here are from the south and from the northeast, you have a fairly high fetch. Sorry, this should in fact say from northwest. That's a typo there. The prevailing winds here were from the northwest, and so you can see the very high fetch values over here relatively, although these are still only about half a kilometer. And here we have then the predicted wave height for a 20 meter per second wind, and this is the wave height in meters. And for this little lake, that seems to be something like a kilometer across, not a very large one. I hope you can see that the wave height is only about 1/3 of a meter maximum, with a fairly rapid wind velocity of 20 meters per second. So wave height, a 3 foot or 1 meter wave is fairly big indeed for a lake, unless the lake is fairly large. Now, here we see a general relationship for the effect of fetch on wave height, and here we have fetch on the x-axis indicated in kilometers, so fairly large ecosystems, and then various forces of winds, 4.5 meters per second, about 10 miles per hour, 9.5 meters per second, about 21 miles per hour, and about 20 meters per second, a force 8 wind, 42 miles per hour, which is the one you saw illustrated in the previous map. One needs to go to very high winds and fairly large lakes before you will have very large waves. You can see, though, that effective fetch of 50 kilometers or so at a very high sustained wind can create some waves of substantial wave height. Now, there are other kinds of surface waves that one should be aware of, and these would be breaking waves, swells, and wave grooves. Now, breaking waves are what we often call whitecaps, or moutons in French. They're formed when waves just simply get too high for the wavelength and topple. Actually, they're formed in two different ways. When they get blown up too high, there's too much lift, and the ratio of the height to wavelength is becomes equal to about 1/10 is the critical value. You remember that we learned that the wave height is usually about 1/20 of the wavelength, but if it gets extreme, then they will simply topple over, curl over. And they also can be formed when tops blow off of high waves, and this is the usual way in all but the largest of lakes that we will see formation of breaking waves or whitecaps, is by blowing off of blowing the top of the wave off. Now, there are things called swells, and we know that that the swells tend to be, if instability is formed in some place, it will form a fairly gentle oscillation in the surface of a water body, and the instability depends on the ratio of the height to length, not the absolute wave height. Now, these swells can be formed when you get a whole spectrum of wavelengths formed in an area of disturbance. And those different wavelengths will pile up in various ways so that you'll create oscillations on the surface of the water. Now, these long waves don't break, and they move faster than the short ones. And so you'll often find at some distance from a disturbance, only long waves. And so if you're seeing swells on a fairly large lake, chances are this is from some storm somewhere that has created a spectrum of wavelengths of waves and created this oscillation on the surface. Another thing you'll see often, and you'll notice this if you're out in a boat on a very wavy day, that you'll get wave groups. And these are formed by interference between waves of similar but not the same wavelengths. And these wave groups tend to move at a velocity of about half that of the waves, and that has to do with the way different wavelengths will interact with each other. Now, rotational forces in waves tend to dissipate with depth. So, and I haven't mentioned this before, here we have a standard sort of oscillating waveform. The water here is oscillating along with the wave as that wave moves forward. Now, the water underneath it has to balance the energy, and there's friction of this water on the water below, and will have a tendency to rotate in the opposite direction, and while dissipating force, and then another rotational force dissipating in both size and power with depth. And this is why you will often see ripples in sand as, from wave action, is that because of these decreasing sizes of sort of spinning masses of water. Sometimes these waves will run into the shore and they'll dissipate their velocity on the shore. And when they do that, they tend to pile up the wave, but they also will do a fair bit of work on the shore and dissipate their energy, resuspending sediment and moving it forward or up and down or in an oscillating fashion. Here we have, again, deep water waves not affected by the bottom. The deep water waves hit the shore and begin to pile up their energy and the water, and oftentimes you'll get breaking waves at the shore because of this piling up, so that the wave height becomes too great to be supported by the relatively short wavelength. Now, we talked about the sorting of bottom sediments before, and faster velocities, of course, can move larger particles. And I also mentioned early on that you can tell a lot about what kinds of winds and wave action there is by the kinds of sediment you find on shores. This is another image from the Hutchinson and Janssen book on lake sedimentology for about a strong breeze, a force 6 strong breeze at 14 meters per second, or somewhere around 30 miles an hour wind. And this shows how much effective fetch it takes down here at various depths in meters to move different kinds of sediments. Now, two things you can judge from this is that if you have a very short effective fetch, it almost doesn't matter. No sediments will be moved. And this is why you find in very sheltered systems no focusing, no movement of the very finest particles, and the shores tend to be covered in very fine materials because none of it has been moved away. However, as you increase the effective fetch, that distance the wind can work over the water, then you'll get coarser and coarser sediments left behind. And these are the waves, how the wave sorting works. And as you get very large effective fetches for the same velocity, even at fairly great depths, you'll be moving away small particles and leaving the large ones behind. Remember that the particles you see are not those, usually in lakes anyway, those that have been brought in, but those that have been left behind and deposited, left behind or deposited. And so usually you will, if you find very coarse sediments, rocks and gravel and so on, it means there's a substantial amount of fetch. You'll almost never, of course, find a sandy beach or a coarse sandy beach or a gravel beach on a very small lake, simply because you don't have enough fetch to sort those sediment particles. Here's the maximum fetch again on this same kind of constructed lake that I worked on, and this was to help them determine where we could keep a beach. There's some places you can't keep a beach, and we use this to determine determine where one could establish a beach on this in this little lake. Here's the wave height from a brisk wind. Again, about a third of a meter over here, a third of a meter over here. And then this is the kind of maximum size of particle displaced by that same brisk wind. And you can see that there are areas where where you will be able to move coarse sand away, but areas also where the brown and blue simply won't even move silt and clay. And this will tell us where you'll get the buildup of certain kinds of sediments and the cleaning of certain other kinds of sediments. Now, this, I hope that you have observed this phenomenon somewhere in your looking at water bodies. This is a lake that I've worked on a fair bit. But what you see as you look down on this lake are streaks of foam. And these streaks of foam are not from boat pollution or something like that. They're places where you've gotten organic matter built up between cells of rotating water created by a phenomenon called Langmuir circulation. And I'm going to show you how that works. Now do recall that as the wind blows on the surface of the water, it creates currents. And those currents will move forward, but because of vorticity, they'll tend to rotate as they actually rotate as they move forward because of the same effect you see in a swirling toilet or a funnel when water's draining quickly out of it. It will tend to spin, and when it spins, you'll have essentially, I like to think of it as sort of a long sausage or long cell of water that's turning, but when it's turning, when one of them is turning, let's say clockwise, an adjacent cell has to turn counterclockwise to balance energy. So it'll always be turning with adjacent cells, and these are Langmuir cells, Langmuir, and they will move water forward with a sort of a vortical type of transport. And you can imagine that if you have two cells of water that are turning in opposite directions, you'll have a tendency to leave floating material in between them in large streaks. And that you can see here in this the left-hand side, and this is also illustrated in the calf text as shown here at right. And you'll get streaks and buildup of foamy material and organic material in between those cells. And that's what forms these streaks, are adjacent Langmuir cells, rotating water. The water obviously was moving this direction. We know that because the water was moving that direction, that the wind velocity, wind had to be coming from this direction so that those surface currents could move in some right-hand rotation or clockwise rotation away from the wind velocity. So those are Langmuir cells. They're actually used in cleanup in oil spills and so on for trying to aggregate together various pollutant materials, and then you can vacuum them up at the convergences of these Langmuir cells. Langmuir circulation, well, the downwelling velocity can be about 0.85% of wind velocity. So this is about a quarter of wind-induced surface currents. The spiral asymmetry, Windrows materials like oils and stuff, and so is used in mitigation sorts of effort. The formation is due to an interaction of vorticity, swirling in the wind-induced currents, and wind-generated gravity waves that get that vorticity moving. Next, I'd like to talk about the effect of prolonged wind on thermal structure of lakes. And here we have, and this is Lake Windermere over here, and this is a diagram of the cross-section of Lake Windermere. And here what we see is, and this is supposed to be a cross-sectional area, so the wind begins to blow, and the dark water down here is the hypolimnetic water. What we see is this epilimnetic water moving across the lake, because of the surface current flow going 3% of the overall wind velocity. You can see the epilimnion being thickened over here and hypolimnetic water moving backward across the lake over toward the other side, causing that water to move up a little bit. And at a certain point, if the wind blows long enough, you can create upwelling, just like Dr. Richards was discussing in the small video segment. You can have an upwelling where the hypolimnetic water is actually exposed at the surface. This is important because hypolimnetic water is often very rich in nutrients and very poor often in gases, and it can cause degassing of hydrogen sulfide, a variety of other things. But the point is, you basically moved the entire epilimnion over to one side by prolonged wind exposure. Now, at a certain point, we stop the wind. Winds tend to go down in the evening, so let's say the wind goes down in the evening. Then something happens. We've gotten an imbalance. We've basically swung a pendulum way over to one side. And it's going to try to get back to where it was in some sort of way. So what happens is, and here we have the beginning of this cycle, this water is tipped in this direction. And what it's going to try to do, this hypolimnetic water, is going to try to move back to the other side to reach an equilibrium. And the epilimnetic water is going to have to rush back to the other side, to balance the loss of the hypolimnetic water. And here we have high velocities moving of epilimnetic water and pendular motion. It overcompensates because it's got too much energy. It'll actually rock the hypolimnion back up on the far side again, and then it reaches a stopping point, and it begins to oscillate back the other way. And it'll rock back and forth over time until the energy has dissipated. And this rocking back and forth of the hypolimnion is called an internal Seiche. And now there are also external Seiches where the movement of this water across from one side to the other will tend to actually pile up a little water on this side, and that water will rock back and forth at the surface. Those surface Seiches are dissipated much more rapidly because of the very high rate of friction between air and water compared to the drag that water exerts on water. So that's how a Seiche gets started. Now, strong wind forces lead to long-standing waves called Seiches. The most conspicuous are surface Seiches, where you can actually see some movement of water back and forth. They're usually hard to see because of other kinds of waves. These are called barotropic waves. And you can sometimes see them at ice edges around lake melting. If you will have some rocking started at the lake surface, you'll see that the lake looks almost like it's breathing. It'll move the water out and move the water back. Those are the most conspicuous. Less conspicuous, but of greater amplitude, are internal Seiches, and these are called baroclinic waves. And those are the ones where the hypolimnion will essentially be rocking back and forth. Now, the period of surface Seiches can be calculated, and I won't in any exam ask you to reproduce this equation, but I would like you to understand what it means. And this is the period of a surface Seiche in the first mode of a surface Seiche. And here the period T is equal to 2 times the effective basin length at the surface, divided by the square root of acceleration due to gravity times the mean depth of the basin. So what this means is that long basins take longer to rock back and forth than shorter basins, and deep lakes take a shorter time to rock back and forth. So I give you an example down at the lower right hand corner. If you have a effective basin length of 1 kilometer and a mean depth of 10 meters, the period will be about 202 seconds, so 3 to 4 minutes. So you can tell that these will have a fairly slow amplitude. It won't be just wiggling back and forth, but will be moving back and forth over a period of minutes usually. Now, obviously, the longer basins would have a longer period, and smaller basins would have a shorter period, and so on. Now you can sort of visualize this again. This is the cycle of an internal Seiche, but we've already seen this once. But this is a little bit bigger graphic. Might be a little bit pixelated on your screen because of reduction of the video size, so that it doesn't bog down your viewing device. But here we have the wind begins. We get wind to several steady state. We can have again some kind of a possibility of an upwelling. We hit a sort of a steady a place where there's sort of negligible flow. When the wind stops, then there's no flow for a second, no flow in the hypolimnion, but then this time we get backflow of epilimnetic water and return flow of hypolimnetic water. We come to a maximum flow velocity is when the thermocline is level, and then we basically get oscillation back and forth of that entire basin, going through periods of no flow and maximal flow, very much like a pendulum. The period of internal Seiches is a little bit more complicated, but only complicated by differences in density between the epilimnion and the hypolimnion. This is what the equation looks like. Again, we have T is equal to 2 times the effective basin length, and then a more complicated equation down at the bottom that includes both the density and depths of the epilimnion and hypolimnion, both of which have an effect. And what this means is that longer basins, again, take longer, and deeper basins rock faster, as we saw in the previous equation. But also lakes with bigger differences in density between the epilimnion and the hypolimnion rock back and forth faster. And this is basically the same equation used for surface Seiches, except that specific gravity and thickness of air were ignored. Now, the Coriolis effect also acts on internal Seiches, and you can imagine this, that these don't simply rock back and forth like this, sort of back and forth and back and forth, because anytime water is moving in the northern hemisphere, it is curving to the right, and anytime water's moving in a straight line in the southern hemisphere, it actually is curving to the left. And so you will get the here we have the initial wind force has tipped this hypolimnion. We have then the flow directions, water flowing back this direction, water flowing this direction. Again, in the hypolimnion, twisting always to the right, so they're twisting away from each other, which then will cause that thermocline to actually rock back and forth and sort of spin in a spinning way as the energy is damped out. It spins very much like a can lid. If you drop it on the ground, sometimes they will spin and rock back and forth at the same time. And the net effect is very much the same. The thermocline is rocking as it twists. Now, internal progressive waves are another sort of wave of interest. And I mentioned those earlier on when we were talking about the various kinds of energy in aquatic systems. Just as we have, we create waves when we are moving air across the surface of water. If we're moving the epilimnion across the surface of the hypolimnion, then we also create waves, and we can see the directions of the forces in this upper panel, panel A. And what happens is we can form fairly large waves at the surface of the hypolimnion, basically in the metalimnion, and those waves can get so high that they will actually break, and that's what you see here. And these are what are called Kelvin-Helmholtz internal progressive breaking waves, or Kelvin-Helmholtz billows. And I think it's clear to you, or hope it's clear to you, that when you have a lot of this action going on, you can mix some epilimnetic water up into the surface waters. And this is why you frequently will see in a lake an increase in production, or sort of greenness of the water and growth of things after a very big storm if it's been very, very windy. You have some mixing of the hypolimnetic water up into the surface mixed zone or the epilimnion. Now there are other kinds of flows and things that operate that move water around in lakes. And one of them would be a turbidity current, and this is happens when we'll get sediment-laden water that has a fairly high specific gravity, higher than the water that without the sediment, and it'll inflow and flow in. And when it flows in, it may sink, causing a turbidity current. That's a current going down the side of a lake that will carry a fair bit of water with it, and you can imagine that it will cause a transport of material into the hypolimnion. Another thing you'll see is a density current, and sometimes we'll get runoff from snowmelt that's often denser than epilimnetic waters, and when that happens, then it'll sink and flow through the lake, causing a large plume, which may flow between layers in an aquatic system. Here over at the left, you see sort of in one of the lakes that I studied, here's a isopleth plot of total suspended solids, and we could see this a bunch of turbidity material showing up down at the bottom. Here you see this by the very densely packed isopleths, and that was caused by a turbidity inflow. Likewise, in this lake system, this is Clear Lake in the state of Iowa in the United States, 3 sampling sites, we had a very big down lake storm transport of water. Here you can see total suspended solids at this station peaking in around June. It took it to somewhere in the middle of July to move down to this site, and moved in August down to this site, and eventually came up the slope of the lake and flowed out the eastern end of this lake. So these are turbidity currents that are caused oftentimes by excessive storm transport. There can also be currents that are generated by river flow, and I mentioned that in actually the previous couple of slides. And this is when inflowing river water flows through the density layer in a lake that's most similar to its own. And there are 3 types, and obviously there are 3 types. The water either goes over, it goes under, it goes between, or through through a lake, depending on what the thermal stratification is and the temperature or specific gravity of the inflowing water. So overflow would be inflowing water as water density is less than the lake water density, so it would simply flow over the top. And I've seen situations where we get warm inflow in the spring time and the water simply flows in the inlet across the top and out the other end without mixing with the rest of the lake. Underflow occurs if the inflowing water density is greater than lake water density. You can imagine this if you'd have an extremely cold storm or ice or glacial melt that would be very cold in the summer. It would tend to flow under the ecosystem if its density were at around 4 degrees C. And then interflow, inflowing water is where the inflowing water density be greater than the epilimnion, less than hypolimnion. It seeks some level through the lake and can flow through. Through-flow patterns can change seasonally as the relative temperature of inflow and lake will change. So there are different time scales of mixing that act on lakes, and this is again from the CALF text. And these are all marked with the various rates of mixing or time scales of mixing. Winds can change on the half hour to the weekly basis. Big storm systems also can have time scales from half hour to years, and heating can change in minutes to days. And what this means is that horizontal mixing is sort of on the scale of about a day, usually mixing across a mixed layer. Metalimnetic horizontal mixing is less because there's less water movement, less turbulence, and horizontal mixing in the hypolimnion about the same. It can move horizontally. Now, vertical mixing can mix sort of on the half hour, a very short time frame in the epilimnion, but mixing in the metalimnion and vertical mixing from the hypolimnion, it takes much, much longer, and usually is on the 3-month to, well, in a dimictic lake, of course, the vertical mixing would be on the scale of about 6 months. Every 6 months it would mix top to bottom in the hypolimnion. So finally, a summary on the lentic water movement, waves and currents and so on. Wind is the main force that moves water, nutrients, organisms, and sediments in lakes and ponds. And you should remember that surface currents can be quite substantial. They can be like 3% of wind velocity and they'll move at about 45 degrees to the right of the wind velocity in the northern hemisphere and the opposite in the southern hemisphere. The size and energy of surface waves varies with the wind, of course, with fetch, that is the distance that wind can act across the water, and with water depth. There are other things that go on, circulation patterns that are quite important. Langmuir circulation is one of them, and this results from the interaction of surface currents and waves and vorticity. And then there are the very important standing waves, actually some of the earliest phenomena discovered in aquatic systems by Forel in Lac Léman in Switzerland. And these are standing waves, which are Seiches, and they are very high in energy, or can be, and they can be expressed at the surface or at the internal way. So there also are internal progressive waves, and you should remember about Kelvin-Helmholtz billows, and their importance is in remixing hypolimnetic water into the epilimnion. And then there are various ways that external inflows can cause overflow, underflow, and interflow, various kinds of movements. I hope that you've gained some understanding of the understanding of water movement, and understand how important it is to the transport of materials and the renewal of material, and also to the kinds of environments that organisms encounter in aquatic ecosystems.